3, 2, 1, go. We're live. This is Retraice segment number 86 for Sunday, December 18th, 2022 at 10 p.m. Eastern, 7 p.m. Pacific. Retraice is about what's going on out there. The short answer to that is computer control. The long answer to that is, oh, golly. The long answer to that is strategic, natural, and artificial intelligence, and Retraice is for outsiders, and outsiders are not players, and the computer control game is player-oriented. If I script it, it's boring. If I read it, it's boring. If I think of it, oh, it's still boring. All right, none of that. Today, you should be jumping right into the middle of a series here. This is your first time listening to or watching Retraice. Good for you, but you might want to start at the beginning of at least this series. We're in the December to Remember Math and Code event. AIMA4e, Artificial Intelligence, A Modern Approach, Russell and Norvig. We're going to be studying a 6-month deep dive, January to June inclusive 2023, but December to Remember Math and Code, because we need to be able to do the math and we need to be able to do the code. The scribba, the typa, not just the yappa. All right. Today, if you're not down with this, we're just going to read code and annotate code. I'm not going to tell you things that I've figured out already. I'm going to figure them out as I go. Some things I've figured out. If you're not down with that, go do your own thing. It's cool. But if you are down with that, hang out. But if you're not, go away. Don't be one of those people. All right. First things first, though. Just a correction from yesterday. You're looking at Retraice notes number 85, Re86. In the look ahead. No, not in the look ahead. In the best first search implementation that we examined, I said at one point that after this while loop completed, the frontier would be updated, and we would go back up to this line. That's not the case. The frontier gets updated where? Down here. It's the last line of this while loop. It keeps getting updated while it's going through the frontier. If it finds the goal state, then it returns that node that has the goal state. Otherwise, it finishes the frontier and then it returns failure. Okay, I just wanted to point that's corrected in the notes for Re86. You're listening to and watching Re86, but I just wanted to call that out. Okay, I do make mistakes. I should not be your artificial intelligence engineer, your software engineer, your programming teacher, your mathematician. I should not be any of those things. But I'm the dude you can hang out once you have all those other things in place. Or even if you don't worry about it. You don't need all those other things. All right, so what are we doing? Are we doing code here or what? I mean, we're just talking, we're yapping, or are we doing code? All right, so what you're looking at here is our source file. You can get to our source file if you go to our GitHub, and you'll see it here. Re86 is the directory. There's a directory for each segment. We're in Re86. Everything's well preserved. So if you need that, you have that. Here we're looking at it, and I should also say, I use the tools I like to use. I use Tmux and Emacs. There are arguments for and against using these sort of old school tools to do this stuff. I like it. It's just how I roll, man. I can tell you, I lived my whole life this way, doing this sort of thing. But you might really want to be in a GUI environment. You might want to be in an IDE, integrated development environment, that's graphical user interface and easier than this, and there are upsides to that. I don't want you to think, I'm not one of these Emacs, Tmux people who is saying this is the only way and there's never been an improvement. Of course, there are advantages, but this is just how I like to roll. You don't have to roll this way. At the end of the day, we're just dealing with text, right? We're dealing with ASCII text in human readable files. We're dealing with source code. That's all we need. That's all we need to just get along, right? Okay, so now what I've done here is I've split my Emacs window here, or frame, into two window panes or windows. I don't remember if these are called window panes or windows. And then we're also going to be looking at another frame. So this is the same file, just further down in the file. So if we go to RouteProblem, you can, RouteProblem. So you can see here, this is, okay, if we look here and here, we're looking at the same RouteProblem thing here. Okay, this class. The reason I'm doing that is just so I don't have to keep scrolling all the time. So we'll look over here when we want to look at the class. Oops. Oh, stop it. Just stop it. Don't do this. We're in front of company. All right. The map class, and then the specific Romania map. That's what I'm going to have open over here. And otherwise, what did I do? Oh no, I just closed it. Did I just close it? Oh no, I don't remember how to open it. 5, 2. Oh, I'm getting good. Okay. I'm not really good with these panes. That's why I just closed one. Okay, so are we good? Are we good? Jeez. There we go. Let's do class. Okay, good. And we do put that at the top. Okay, and then we do class back. Okay, we're back here. Good. Okay, so this is our original class for our problem objects. Okay, and I just wanted to keep that at the top of the screen because it kind of corresponds to this over here. This is from Retraice notes number 82, our first segment on the best first search, right? Yeah, best first search implementation. And it gives us the essential ingredients for formalizing a problem: the state space, initial state, goal state, actions, transition model, which is our result of action on state function, and then action cost function, which is the function that tells us to go from state 1 to state prime or state to state prime using this given action. What's the cost of doing that? So, and that's, we should distinguish action cost functions from evaluation functions and objective functions, which they're not. They're different kinds of functions. Anyway, that corresponds to kind of what we're looking at over here in the, can I just be slick? There we go. And I'm in read only. Good. Okay. Don't want to do any things. So we've got like actions. The actions function takes itself in a state. The results function, which takes a state and action, and then down, not the is goal, but the is goal is part of it too. But the other function that sort of stood out there, jumps out, that's hard, is this action cost function, which takes a state, an action, and then a new state. And in this implementation, so let's do the first thing here. Get out of read only, and we're going to do not done. It doesn't auto. I don't know how to auto complete. Like stars and stuff. I just don't know why. I can't never get that to work. I should. Okay, so that's not implemented. This is come on. This is okay. Is goal, because it's pretty easy to pass an argument when we're instantiating a problem as an object. It's pretty easy to just pass it a goal state, and the goal state is just, we can just check it here using the is goal function. But it's these other three, and we're not doing this one either. Let's just hide that one. We're not doing H, the heuristic, and we don't care really about the string. Let's just keep this simple, okay? We're just going, and do we care about initial? We don't care about updating the dictionary right now. This is the simplest way to look at looking at the object or the class problem, okay? Let's get out of read or write. Okay, and now we're down here to a subclass of problem, RouteProblem. Okay, we talked a little bit about this yesterday. I flashed it. I mentioned some things, but I didn't really annotate or go into it because I wasn't ready, nor am I ready today. That's why it's still not really annotated. I can't fold that because we need that. Okay, this is the main, this is what I was planning on working through today, but time was not permitting. And also, I've been working a lot on, how to present this stuff like this. I feel like there's so much more we can do to present better than what we've been doing, but this is good enough for now. So that kind of subtracted from the time available to annotate and unpack this. But this is no mean feat. This is really the where the rubber meets the road. So first of all, let's just I can't preserve a highlight up here. That's kind of a bummer, isn't it? Because we're within, that's why I use tmux, because within Emacs I can't sometimes get the result that I want. Okay, so this is a re-implementation of the actions function. So this would replace when there's subclass to define a route problem, they're subclassing problem, okay, which is the one that's in the top window. And one of the things that they do is they're redefining the actions method. Why? Well, of course they are. Whoops. Because this is not implemented, okay? We don't have anything really substantive here. There should be lines, okay? If we were serious, we'd have lines here telling the computer what to do once given this state. So in the meantime, we are going to, this is just sort of like a placeholder, as is the results thing. And really, even the action cost is sort of like a placeholder, okay? They're no longer placeholders once you subclass problem and you for a particular kind of problem, okay? In our case, a route problem. This is, I wish I could say I was 100% certain that this is the one we're going to use to solve the Romanian airport problem, but I'm 100% certain of absolutely nothing. So let's just put 99% on this. This is 99% chance the subclass of problem that we're going to use to solve the Romania A to B problem. Okay, and if you don't remember that, let's jump over and just have a little refresher look here. Get from Arad to Bucharesti using a machine instead of your brain. That's the Romania problem in the short version. Okay, so subclassing problem, we redefine the method actions, we redefine the method result, and we redefine the method action costs. What do we do? Well, this is where it gets interesting. So first thing, I just sort of tried to show what it would look like to call this method. Let's say, atab, let's say we define we want to define an A to B problem as a route problem. So we want to instantiate the class route problem as the object A to B problem. Okay, that's just the name for it. The object is in memory. You can't see the object. You can't see anything. You can only see the representations on the screen. This is our subclass of problem. Okay, this is just comments. Right? Like I'm just showing you like what it would look like. And then these are the arguments. Okay, we would have state, initial state, goal state, A to B. We want to get from A to B, and we need a map. This is new. We haven't talked about this yet, and I'm not really at a point where I can explain this well, but if you're curious what we mean by map, just as a little cheat, it's this stuff here. So first, we've got the class of object called map, okay, and it has an initialize method and a lot of attributes like distances, neighbors, locations, and it takes a couple of arguments. You can see, so it takes an argument of links, whatever the links are going to be. We'll talk about that in a second. It takes an argument of locations, defaults to none, and then it takes an argument of directed, defaults to false. Okay, so that's the class of map. And then if we want to instantiate a particular map as a map object, let's say we want to instantiate Romania, i.e., we want this picture, which is a graph of a state space. And remember, each node. Each node in our, is it a node before we start building a search tree? Let's say these represent states. Until we're actually executing search, we don't have nodes and links. Oh, shut up. That's not true. What do I say? 71. Re71. Let's just look at the thing we need to look at, which is me reading a book. A search algorithm takes a search problem, blah, blah, blah. Superimpose a search tree over the state space graph, forming paths from the initial state, trying to find each node in the search tree. So what I'm going to say about in terms of our nomenclature is that this graph of the search space is made of nodes and links, or nodes and edges. Okay, but it's not the same thing as our, it's not open, where is it? It's not the same thing as our search tree. Our search tree, let's do this, let's say command option, there we go. Our search tree, this is gonna be, of course it's gonna load slowly. Why would it, of course, like it's the slowest thing I've ever downloaded in my life. Well, I'm live streaming, why wouldn't it? Why not dial up? Why don't I get the pshee-doo-doo? Why don't I get that sound? Why don't I just send it via post? Or receive it via, I can order it from a Sears catalog. What can we do here to make this go faster? Please, computer, thank you. Neurons, that's not what I want. You know I don't want neurons. I'm not talking about that stuff yet. All right, I'm scrolling down because I don't know what to, let's see, 3.7? 3.7 is kind of the vicinity. Yes, there we go. Okay. So when we start to draw a search space, are you looking at the, yeah, you are. A search space, if we start to expand our search tree, this is the maroon part is the search tree, the purple part is the state space. So we have to distinguish between those things. I'm going to leave this open because that's there and that's there. Okay, so our state space can be represented as a graph of nodes and links, but our search tree are the nodes and links we're going to be talking about, or nodes and edges we're going to be talking about most of the time. Why did I start talking about this? Because we are talking here about the map object, or the Romania object, which is an instantiation of the class map. And in this case, we've got stuff. Look at all this stuff that looks useful or carefully assembled. Okay, what that stuff is, well, we're going to have to walk through it here. But the short version is it's the coordinates of these nodes, which are states in the state space. So the coordinates of the cities, but they're states in the state space, and we're representing them here as nodes. But in our search algorithm, they're not, in our search implementation, they're not going to be nodes, because a node is in the search tree has history to it. So like this node can correspond to this state, and it can represent the path from here, and it can also represent the path that goes via here. So the nodes, you got to be careful. It depends on, when you say node, it depends on your context, what you mean by it. But anyway, we want to represent all these coordinates, and we want to represent all these edges, which are distances. And I think they said that they're in miles. I don't know if they use miles in Romania, but they use miles in AIMA4e talking about Romania. So what do we have here? Well, we can understand or unpack this. Okay, so first of all, notice that this is a dictionary, okay? The braces in Python mean it's a dictionary. That means it's key value. So in the first line, we have, well, let's do the last line because that's what we're near. P and R, these are our key, okay? This little tuple, okay? That's our key, and then the 97 is our value, and you call it a key value pair. And you basically use dictionaries to, if you have the key, to look up the value. You don't use dictionaries to have the value and look up the key, because I think it's roughly a mathematical function. It goes one way, not the other, not necessarily the other. Okay, so first notice that this is a dictionary. Don't worry about what the comments say right now. And then notice also that this is a dictionary. Again, key value. So if we start with A, our key is A, which is, that's going to be a state, or that's going to be a state in our state space. And then it has a value. What's the value? That's going to be the coordinates in this case. Okay, so this is a map. This is the class of object. This is a class of data, or a class in object-oriented Python that structures the data that we would need when we want to create a particular map. And in the comments here, they explain the two arguments. So where do they give it? Where does it say map? Map. Yeah, here we go. Okay, so it takes map, links, locations, okay? And, whoops. Okay, so I just copied these comments down to the particular example where they're used, okay? So I don't know why this isn't syntax highlighted. I think my highlighter is a bit confused by all the comments. But what this statement right here, plus everything down to here, is saying is we are instantiating the class map as the object Romania, and we're giving it two arguments, two giant arguments. One is a dictionary, and the first one's a dictionary, and the second one's a dictionary. The first one corresponds to what in the class definition they call links. That's the first argument. So if we go links, oh man, we're gonna have to go right there. Okay, that links is, let's do it again, links, and, oh geez, links. I'm gonna get better at this, don't worry. There, that, okay. Well, not that, but it's this. This is the links, okay? So we have this O comma Z 71. Let's see if we can find O comma Z and convince ourselves that we know. Look at that. Oradea and Zerind 71. Do we see any other 71s? I don't see any 71s. Let's see if we can increase our confidence in our interpretation. L comma T is going to be our key. Our value is 111. Let's see if we can find L Lugaj Timisoara 111. Any other 111s? I don't see any other 111s. Okay, we won't be pedantic here. So what these key values are you've got two states, and the first and the second in a tuple, and then you've got the link between them, and it's a distance in miles. That's a pretty safe interpretation of that. What are these locations? Well, we can't be as confident in these, but let's say A is Arad, okay? There is probably another A somewhere, but it might get a different, maybe they were careful. I think they carefully didn't duplicate first letters. Okay. We're going to say the coordinates of Arad are 76 at the x-axis and about 500 at the y-axis. Okay, so maybe the origin is here, so we go to 76 and go up 500. And then let's look at B, because B should be about 500 and then maybe like 50. So let's go see if we're right about this. Where's B? Okay, 400 and 327. Why? That's not right. Why is B 400 and 327? It shouldn't be that high. Okay, what else is at 327? Because maybe, we've got the, oh man, that doesn't seem like it should be. No pun intended. B, 400 at the x-axis and 327. So it's 200. It's about half the height of Arad. Does that seem right? Oof, no. Unless the origin is way further down here, which it very well might be. Let's do one more. So if Bucharesti is at 327 and Arad is at, so basically like 300 and 500, this should be 400. The Rimniku whatever should be at 500 on the x-axis. Let's look for an R. Oh man, that just maybe these coordinates are not true to the graph in the book. I mean, there's no graph of them in the book, or there might be a V. Is there a V? Oh no, what did I do? There we go. V. 500, that's what it is. Okay, that's got to be it. So 500, 400 is that Rimnu, because there's probably another R. Is there another R city over here? Look for an R. Say a prayer so I don't have to keep thinking about this. No, there's no R. But it looks like that one's smack dab in the middle. What about F4? Okay, so let's see if Mehadia is the same Y value as Bucharesti. Okay, so an M. Why is there no M? Oh yeah, there is. Okay, so M, the Y value is 343 and Bucharesti is 327. Okay, right? So if you see 327 there, and that's pretty close. Okay, enough. Anyway, you get the idea. We're going to just, until we find evidence that those coordinates, and even so, I mean, even if the coordinates don't match, like this is just their implementation of a map. It doesn't have to be the map that we see in the book. It doesn't have to be true to that, but I think it probably is. But we have to learn, because they're just using single letter representations of the cities. We might get confused. Might get Ben done. All right. So that's the map. That's a little bit of just getting a feel for the map. There's this outside function, multimap. We'll get into all this, oh gosh, we're at 24 minutes already. Holy crap. Okay. No, I can't do that. I got to do it. Okay. So it takes a map. Yeah. See, this is why I couldn't do this in a day. So the subclass, if we're going to subclass problem, and we're going to implement. We're going to instantiate route problem, the subclass of problem. We're going to do it something like this. We're going to say A to B problem equals route problem with the arguments initial state A and goal state B, and the map we're going to use is simple map, and our simple map is going to look a lot like Romania. You know, it just Romania. It's probably going to look like it's going to be the same map. Screw it. Well, I'm not going to use a different map, but for now, we're talking about a different example because that's, you know, I'm using different blah, blah, blah. Okay. So, okay, let's just read a problem to find a route between locations on a map. Create a problem with route. Yeah, this is so this tells us what I just did above with the arguments. States are the vertices, vertexes in the map graph. Actions are the destination states. Actions are the destination states. See, I wondered about this. Okay, so, oh, that's stupid that it does that. It's me. It's my fault. It took me a while to kind of figure out like what these dictionaries were. And did I screw this up? I did. Did I delete? No, I didn't. No, that's a comment. That's okay. You know, I wrote a couple of comment lines here trying to figure out what this was until I noticed that it was in the description of the class definition of map. So they're saying the actions are, actions are destination states. So, okay, maybe, like I interpreted these as the state, okay, hang on. So what does that mean? The arguments for, okay, so it looks like, hang on a second. I need to clear my head here. If you instantiate a map, you give it links and locations, and maybe you say whether it's directed, but we're not going to do directed. So what I'm doing is directed. Okay, I'm just thinking about this part right here. So we initialize or instantiate a map as an object. We give it a dictionary of links. It can be either the tuples that they say in the comments just above, or it can be a dictionary of two vertices and a distance between them, right? And then the locations aren't the state space. Okay, let's just, I'm not there yet on this one. States are the vertexes in the map graph. And actions are the destination states. Why am I having such a hard time with this? This is because I'm on camera. I'm not on camera. No, I'm on camera, but I'm having a hard time juggling this in my mind. But this has happened a lot as I've been reading through this. States are the vertices. That would make, yeah, okay, so I have it right here. Locations. These are, oops, jeez. I have it right. These are my comments. These are the locations. And so the links are the actions. Yeah, I have it right. I haven't absorbed it. Like I comprehend it when I'm reading it, but then when sometimes, I mean, it's not in my brain yet. I haven't really like absorbed it. States are the vertices, actions are the destination states. No, I don't. These aren't destination states. These are links. I guess this is like going from, I don't know how to say this in English. That's what I'm struggling with. How is this? That's what I'm struggling with. Actions are destination states. This is not destination states. This first dictionary, the links are, if they were destination states, they would be one thing. I guess you have to, in order to look up an action, you first have to provide the state that you're in, or the state that you're in, the state you want to be in, and then and this is weird. It's weird doing this live. Like I can't. Half my brain is devoted. This is part of why I'm doing code reading now, and we're going to do a lot of code reading because I have to get used to ignoring you. Like right now, I am totally paying attention. Half my brain is devoted to how I sound, and I'm not losing myself in the code, which is what I need to be doing. So just understand that that's part of, and it's going to be part of what you do when you do this stuff. You're going to have distractions, and you shouldn't have distractions like a live YouTube channel while you're trying to comprehend basic, simple code. Okay. I doing this is going to be a much easier way of sort of getting it, absorbing it. But that's the problem. That's the reason we're not just like executing toy problems is because we tried that. Like we talked about that yesterday. Putting together a toy problem is not easy. I think it'll be easy once we've done the one that they've implemented. Sort of like let them hold our hand through the whole. What is it like? It's like, it's like building a toy car. You know, you just tell a kid, build a toy car. Don't build a full car. You just build a toy car. Well, you need at least 2 axles. You need 4 wheels. Maybe you need tires. You need a body that connects them, keeps the axles parallel, and you need clearance and all these things. It's best to just do a pine wood derby. Did you know about this pine wood derby? You give kids a block of wood and a couple of metal, what do they call those? Well, they're axles when you use them, and then the wheels, and then they just do it's hand holding. Okay, we need some hand holding here, and that's why we can't implement a toy problem. But even the simplest hand holding version of this requires a lot of jumping around. I find, I've found. So anyway, that's what we're wrestling with here. So we have to get under our fingers, under our minds, that the actions in our Romania map are destination states. And it's you can see why it would be hard. It would be an unusual representation or an unfamiliar one. How is this an action? Like when I first looked at Arad, and I'm saying it like it's Arabic. It's not Arabic, but that's how I heard it said. It was closer to that than Arad. When I first looked at Arad, and I thought, what's the action applied to the state Arad that gets you to Zerind or Sibiu? And it's like, first I was like, well, turn left and go. But really what it is go to, like the best level of abstraction is go to Z or go to S or go to T. So those are the actions available at the state Arad. Go to Z, go to S, go to T. What does that look like in code? Go to this, go to that, do those actions. We're being told that that's an action. If you're at O, go to Z, which means traveling 71 miles. Or in the case of Arad to Zerind, let's find, A to Z. Look, that's an action. If you're at a state, I can give you. This is what our map and our problem object are going to tell us. If you're at a state, I can tell you the action you need to take to get to another state. And what did we just? And in this case, it would be if you're at. Oh, geez. No. Romania. No. Romania. Okay, there we go. If you're at A and you want to go places, you can go to Z, you can go to S, you can go to T, ZST, right? ZST. And now the thing I'm wondering about is how they described, this is a transition model. Is it a transition model? The result of state and action returns the new state. The way that this is described, it's more like the action cost function, or at least it covers both things together. Okay, so if we look at A to Z here, we're not providing a state and an action. Actually, if we were providing a state and an action, so the transition model would look like this. We provide a state, okay, so that our first argument into our transition model would be this key value pair here. And what does that look like over here? So our transition model is our is a result, right? Yeah, the result function. So it's going to want a state and an action. Okay, this is helping. This is helping. I'm starting to get it. Okay, so let's get out of this. And no, I don't have autofill on, do I? Autofill mode enabled. No, I don't want to do that. Enable. Okay. In Romania, state is XY's, and action is just A, B, and miles. Okay, I'm just so I don't forget about this. Now, so let's say we want to know the result of an action. We want a transition model. We want to go from Arad to another city. We need to, in order to do that. Damn it. In order to do that, we need to provide a state and an action. Well, that's exactly what we have over here in our map. We have, I don't know why they put the actions before the states, but we have a state, which is the coordinates of Arad. Okay, so we would provide that as an argument, as the first argument. And then we want to go to, let's say, which one do we keep? What do we like here? We want to go to Sibiu, the one at 140. Okay, so let's go to Sibiu right here. Okay, so we're in Arad. We want to go to Sibiu, and it's going to cost us. And now I'm not saying cost, like that is the cost, but that's not. I don't know how the action cost function is going to differ. But this is our second argument. Okay, this key value pair is going to be our second argument in the state. In here, it's going to be the second argument. Okay, the first is just the name of the function, or the object. So we put that in there, but we never write it, not in the argument space. So the first one we write is the state, and the second one we write is the action, and that is. This is the action. This is the action. A to S is the action, 140, and then A, the state, is the coordinates of A. Okay. So this is why the map is crucial, because we can't even make sense of, this. So up here we're talking about the parent class problem, but down here this is a subclass of route problem. It's much more tailored to our needs. Okay, route problem is a subclass of problem, and we're doing actions here. And our action. Oh yeah, result. Yeah, results takes two states. Yeah, okay. See, the action function takes a state and tells you what actions you can do. So in the case of our map in Romania, it wants a state. So what state do we give it? We give it A. Okay, that's the argument we give it is A. And then what it's going to do is it's going to look up in the links dictionary. It's going to find all the A's. It's going to find that one, and that one. And those correspond to Z, S, and T. Okay, what does that correspond to? Okay, Z, S, and T. So if we call the action method on our object A to B problem, or whatever they're going to call the problem, I forget. We want to know what actions we can take from a rod. We can go to Z, S, or T. Okay, so that's what that's going to do here. Just by passing a state to this method, we're going to get those three actions returned. Now, how do they do it? Well, this is a little bit harder to read, but it's basically going to take the object, our A to B problem. It's going to look at the map of our A to B problem, and the map of our A to B problem is associated with it. How the problem? Oh, it's here. So map, look, see this? Okay, in the comments, they tell you how to create a route problem object. The first argument is the starting state. The second argument is the goal state. And the third argument is a keyword argument, map equals map. And in our case, it's not going to, okay, I got to write this too. So let's do, I mean, here we'd pass the map Romania. Okay. And then down here, our A to B problem with the method map would return neighbors of A, neighbors of the state A. That's what this is. So A to B problem, the map, which is Romania, right? Because it's here, it's being, our Romania map is being assigned to this variable value or this attribute value. And so down here, then, it's looking at the Romania map. It's not looking at something called map. It's looking at what we're calling map within the object, but it's looking at the neighbors in the Romania map of the state that we passed to it, which was A. So what is that? Oh, you got to be kidding me. Oh, no, that's okay. So what does that look like? What are the neighbors? Well, that's a this. This is an attribute of the map object. Is neighbors, okay? And it's defined as the function, the results of the function multimap on links. Now, forget what multimap is for a second. We're going to talk about that in just a second. Links is this, okay? This first dictionary is the links, which is also, what? I'm not trying to do anything. I'm not, oh, my hand wasn't aligned. That's this, okay? So we're going to pass this into links here, and pass it and then to the multimap function. Now, what's the multimap function? I don't know how to explain this. I don't know. This seems to me like it takes the pairs and turns them into a dictionary. Dict definitely seems like, I mean, that's one way of initializing a dictionary in Python is using dict and then parentheses. So like if you, let's do this, seems like initializing, oh geez, dictionary per alt-off page, thusly thing equals dict, and then like it's a function with no argument, okay? That's, I'm going to put the alt-off page in there, but I just read that earlier today, so it's fresh in my memory. So you, given the key value pairs, make a dictionary of the key and the value. I don't know why this is like this. It feels like that those dots should be outside of this list square bracket. But anyway, so multimap seems to take the pairs argument, or take pairs, you know, and you have to provide a bunch of pairs, but you would be providing that if you provide either a dictionary, or you wouldn't provide a dictionary to a dictionary. What is it taking again? It's taking the links part. Yeah, no, it's taking a dictionary. These are key value pairs. I guess the multimap function doesn't care if it's taking another dictionary. It doesn't need to be tuples, I guess, is the only other thing it would be. There wouldn't be anything else. It wouldn't be a list, tuple. What's the other kind of data structure? I don't know. Anyway, it seems like this is going to take the pairs of our dictionary, or, you know, it could be other kinds of pairs, but it could be a list of tuples. I guess that's, but isn't that kind of what a dictionary is? No, dictionary, never mind. All right, I'm out of my league here. And what does it do? It's going to set the result equal to the default dictionary function applied to the argument list. I don't understand this. This function I don't understand yet. And then for key and value in pairs, the result should be, I mean, this is just how it's doing it. This is just how it's generating this dictionary, but I don't understand this function very well. Okay, let's leave it at that. So anyway, go back up here, neighbors. We were talking about neighbors, okay? Neighbors gets its definition and content from the multimap function, taking our links argument. And where were we? Yeah, and we were here, okay? So we were in the actions method of our route problem, and we wanted to get the actions available at a given state. How do we do that? We use the actions method on our object. In our case, it would be like typing something like this. Okay, A to B problem is our object in our comments here. We haven't actually done this anywhere. We're going to use the map method on it, and we're going to, and the map method is, or the map attribute. The map attribute. The map is an attribute, not a method. Okay, that's here. It's taken as an argument, and it's an attribute set to simple map here, or it could be set to Romania in the AIMA one, and then it's looking for the neighbors, and it's using that. I've already forgotten what it's called. The multimap function, and we only have to pass it one thing, which is the state. And then we'll get back our neighbors. And then those are what? They're the actions. The neighbors in the map are the actions we can take, okay? The actions we can take if we give the state a rod to our route problem and ask and call a method on it is go to Z, go to S, go to T. Those are the actions we can take, and that's all our action method needs to do. And similar sort of thinking applies to the result function, the result of going from being at state, this, and taking an action. These actions, where do these come from? Well, that comes from our actions method, okay? So once we know the actions we can take on this state, we can go, if we're at a rod, A, we can go to Z, S, or T, then we can provide one of those here. And we want to know the result of that, and it returns the action if the action in self.map neighbors else the state. I'll have to come back to that. We're running long here. This is going to be, but anyway. And then finally, the action cost function takes your first state, your action, and the new state, and what's the cost of it? And it's almost certainly just going to be something very simple, which is if we're going from A to Z, if we've gone from A to Z, or we're modeling going A to Z, the cost is 75. The cost is the miles. Okay, and that's over here in our what? Nope, didn't want to do that. Over here in our first argument, our links have our key value pairs in our links dictionary has these values that are the. So for what did we just say? We were going from A to Z. That's this one, 75. Okay, so that 75 is that 75 right there. Okay. I think that's pretty good. I mean, down here, like, there's a lot more going. There's a lot more, and there's also like not a lot more going on. So they're instantiating the route problem as an object R0 here. Okay, they're passing this problem R0. They're going, they're writing this up so that they want to use the best first search, or they let's see, no, not necessarily that algorithm, because you can use different ones. But we're going to define a problem. Of the problem of going from A to B on the map of Romania, okay, and we're going to call it R0. That's a problem object. Similarly, these other ones, okay? These are all, as they put it, some specific route problems. And once we have a problem, we can go give an argument to, no, this is not, no, that's not what we do here. We get to the point of problem by using the route class, having a problem by using the route problem subclass. If once we have, that, what was it? Like R0, that, then what we do is we go to best first search, okay? So we have best first search algorithm, or implementation of the algorithm. It takes two things. It takes the problem, and then it takes our evaluation function, which we haven't even talked about, and I don't even see code in the initial parts of the AIMA stuff for this. But anyway, you see why the picture for this segment is those gears turning. That's how it feels. Understanding gears turning is what we're doing here. It searches nodes with a minimum of F node. Oh, it's just an F. We might just set F to, I don't know. I'm not going to try that. Think that through right now. And we've already talked, look at all this annotation we've already done on the best first search algorithm. But we did that before. We sort of did it like out of order. It was like we kind of went where our natural English, no, not English, it doesn't matter English, where our natural squishy neuron wetware brains thought we should go. And also I was just sort of working through the order of the source code, but like they structure the source code in a way that makes sense for the long-term purposes of the programmer, not for the, sort of linear, simple-minded podcaster who's reading the source code. So we went through it piece by piece, but we realized as we got to some pieces, like this piece doesn't make any sense and it's not usable until these later pieces come in, okay? And so really, like, it's just a big, long way of saying, if we're at the top here and we just go through all this stuff linearly, we're going to find, and actually, I've got a lot of stuff. Let's see, fold this, unfold all, okay? Oh, this takes a second. I don't know why this function is so slow. There we go. Okay, so now we're at the top of our source code file. And this is not all the source we're going to need. I think it's most of it. But look, we go through all this stuff, okay? We've gone through a lot of it. Stuff where you see annotations, we've covered. Stuff where you don't, we really haven't. And you get down to the bottom where you actually have problems defined down here at the bottom. You've got, a map was necessary, the class of map, because, it's an object, the multimap function, which returns, which helps us find neighbors. Why is it called multimap? I don't know. Look at all this stuff we have to do, and it's not really clear what order to do it, okay? And so when you look at today's segment, okay, this picture is the resolution is killing me. This is not my fault. It's something about in the browser. It does not all anyway. That is what we're doing. There's a gear here and the gear. Which one do you start with? If you're examining this clockwork orange here, which one? Oh, the big one that seems important. Oh, let's start with that. Wait, it's got a little one attached to it. Oh, that's turned by this one. Is that turned by it or is it turning it? Where's the energy coming in and going out? Where's our input and output in this thing? Where is our input and output in these things? I don't know. I can't find it. Okay. But that's sort of code reading, right? It's fun in games. It's the only thing that's not fun about it is when it goes too long. No, it's when you get stuck. And we're not stuck, so we should be happy. We're learning AI code. You can call this AI code, right? This is fancy enough. It's the real weakness of this organization right now is really Python. It's like my Python is just weak. Like I don't find it easy to jump around and follow this code yet, but we're learning and you're learning. Everybody's learning, even though we said we didn't want to do teaching. Look at this. It's like we're kind of doing it even though we don't want to. That's it. All references and all yap, and everything else will be in the show notes. Retraice.com, Retraice.com. Same time tomorrow, 10 p.m. Eastern, 7 p.m. Pacific. I had fun. I'm having fun every time. I don't know about you guys. The other thing is, you're at the end of a long one here, so this is no use to you. But you can always wait for the recap. If you see us going deep dive into this, and you're like, oh, I don't want to go deep dive. I'm going to get lost. I'm going to drown. The recap will sort you out nice and purty. Signing off.